What if a large language model could watch a video and pinpoint the exact frame where a certain action occurs and explain why it happened in real time? Today we're going to dive into a paper called VideoChat, and it's a video understanding model that you can chat with. And it fuses video foundation models with an LLM through a learnable neural interface. Fundamentally, it's going to understand the motion at both local and global levels. And it's going to focus on exactly what matters depending on the prompt you give it to the LLM. And the system delivers on multiple aspects. It delivers on spatio-temporal reasoning. So it's going to be able to track objects spatially and temporally across many frames. It can also localize the action. So it's able to identify the segment boundaries for complex actions. It can also do the causal relationship inference, so it can explain why a certain outcome occurred. For example, a skateboarder that lost his balance because the board tilted midair. So what's VideoChat? So there's two complementary modules. So the first one is called VideoChat Text. And this one textualizes every clip once per second using lightweight perception models. So we have instant video, we have whisper here, we have an object detector, we have an action classifier, so on and so forth. And it generates for every 1 or 2 seconds the caption for the clip, what is the action about, if there's a sound that was produced, so on and so forth. And this narrative is fed into a frozen LLM, instantly enabling interpretable chat. It creates millions of instructions cheaply that will be used later on by the VideoChat embed. The VideoChat embed, on the other hand, sends raw frames through a vision backbone plus a QFormer token interface so that the LLM attends directly to the compact video embeddings. So everything except the LLM is trained end-to-end and is going to give a far richer spatio-temporal understanding in the latent space. So just to recap, the VideoChat here is going to create a very large instruction data set that's going to be used to train the second part. So this part right here is going to supervise on sentences produced by the top part right here. But because of the architecture, it's going to be able to see the full spatial temporal features, both in space and in time. It's going to internalize all of the motion cues, the object interaction, the causal chains that the text can't explicitly verbalize. And because we're supervising on that text, and because the architecture right here is able to see those features, is going to be able to verbalize those features through the LLM. All right, so let's zoom in into the actual VideoChat embed architecture and talk about the models here. So we're going to start with a visual encoder. So that's a transformer. So each frame right here, you can also have some videos. This is your regular transformer encoder. So each image right here is going to be patchified. And then all of these patches are going to be passed through the transformer. And the goal of the transformer is to add more context to each of these tokens containing information about its relationship with other neighboring tokens, both the tokens that are near it or far from it. But in addition to that, we're also going to add a class token right here, which is going to be blank. So it doesn't really have any like inductive bias. And this token is going to learn a general representation of the tokens right here. So it's going to summarize the spatial evidence instead of just doing a naive averaging of the patches. This is going to be a kind of a smarter summarization of the content of the patches right here. And it's going to be later reused in a subsequent module called GMHRA, which we're going to talk about. So once each of these frames are passed through the transformer and they're contextualized, they have an understanding spatially about what's going on in neighboring tokens. We're going to pass it through the GMHRA component, which is the global multi-head relational aggregator, which is composed of two parts. It has a local multi-head relational aggregator, and it also has a global one. This is a very cheap way to actually aggregate temporal information in a short window of time. So think of it as neighboring frames quickly talking to each other about the kind of motion that's going on, but it's very at a local level. And it does this by performing the 1D depth-wise convolution. So this is across the channel, it's not across the space. So it does this on a local level. Then there's the GMHRA, which is the Global Multi-Head Relation Aggregator, which is going to use two things. It's going to use the output of the local multi-head relation aggregator, so all of this local exchange on the temporal scale, and it will allow as well the CLS token to attend to all of the patch tokens right here, and all of this information are going to pass through a multi-head attention, and it's going to enable a long-range temporal reasoning, and it's going to capture object and action level semantics. The output of that is going to output information in terms of the keys and the values. And it's also going to output a kind of a global CLS token that's going to be appended to the token list so that the downstream module, like QFormer, is going to be able to access information from the KNV as well as information from the global CLS token. So that means it can access both frame level and video level context, because the CLS token will have a kind of a summarization of what went on temporally and spatially in terms of the video. So that's the purpose of the global multi-head relation aggregator. Now, why do you have the local and the global multi-head relational aggregator? Because performing multi-head attention is very compute heavy. So we're not going to do it everywhere. So we're going to use the 1D depth channel-wise convolution for these local interaction, and then we're going to have a multi-head attention on top of that to aggregate all of that temporal and spatial information. And the output, as mentioned, is the KNV and class token, which is the summarization at the video level. So if you have a KNV right here, we also need queries on the other side, because that's how transformers, these are the inputs of a transformer: queries, keys, and the value. And so what is QFormer? So QFormer is think of it as an interpreter or an adapter. Okay, it's going to unify this part right here. So these are all of the local and the motion spatial temporal cues, and you have the LLM on the other side. And so the QFormer is going to act like a bridge. It's going to do two main things. So it's going to map all of the visual information right here into the language space right here. But not only is it going to map, but it's going to compress and compact all of the information right here in such a way that it's going to extract the most important things relative to the task. And how will it know what the task is? The task is going to be baked into these query tokens right here. These are going to be task-dependent queries. So you can think of a query token as a kind of a question that's learned during the training. So for example, a question can be, where's a certain object? Where's a car? Where's the person? Or what action is going on between frames 30 to frames 50, for example. So these are questions that are learned depending on the question being asked right here. So you can think of, another way to think of the query, it's like a journalist that's trying to pull quotes from the vision tokens and is translating them into the language space. And by doing that, it's gonna distill. So if we were to feed this straight into the LLM model, you would have about 1600 vision tokens. Okay, but because of the QFormer, it actually extracts exactly what we need depending on the task. You're going to end up with about 100 tokens. So it's not only compressed, but they're also adapted to the language. So they can actually be concatenated. So these are language-friendly tokens and can be inserted into the prompt that is fed into the LLM, because now it's able to understand these tokens. So to summarize, instead of about 1600 tokens that speak a different language, the vision language, you have a compressed size that the LLM can understand, and it is as well thanks to this linear projection right here. At the end, we're going to have these compact video embeddings right here that we can just plug into the prompt. And so you're going to have your text prompt right here. You can add your video embeddings right here and feed that to the LLM, and you're going to supervise on the answer. So what about the training? How do we train this? So there's two stages for the training. First of all, there's an alignment stage. You can think of this as teaching the model just the basic vocabulary. The goal is to get the model to talk in general about the visual content of what's going on. And the way you do that is you feed it 10 million video text pairs and 15 million image text pairs. And you equip the model at this stage with a kind of a vocabulary to talk visually about the images or the videos. The second stage is the instruction tuning stage. And this is more about teaching the model to be useful when the user asks something specific. And we're going to focus on things like when did something happen, why did it happen, or what's going on right here. So these are question and answer pairs that focus on the temporal or the spatial or the causal information. So you're teaching it to answer real questions right now. So this part is how you make it useful. And the data set is much smaller but higher quality information. So you have 7K videos and 3K images that are detailed in description. You also have conversation type of data, and you have 2K images mainly for the causal chains. One thing they did in this paper is a kind of a regularization trick. There's another paper called Unmasked Teacher, and it occasionally shuffles a single still image into a clip. So it treats an image as a kind of a video with only one frame. What this does, it helps the model to prevent an over-reliance on motion cues, and it leverages the abundant high-quality image text pairs that is available. And so that is what this paper is about, VideoChat.